Okay. What's that? Oh, yeah. Let me get that turned on, too. That's what I was looking for. I have just a couple of announcements I wanted to make. I was hoping more people would be in by now. And but hopefully they'll listen to them here. I guess the main one is the fact that they have finally, I think I've been telling you all term, U4 students have all completed payment. It's the one student who hadn't been here, not completed payment. She has now been removed from the roll. So as of sometime between yesterday and today, they removed all non-paid students from the roll. But that doesn't affect anyone in this class. But if you're taking any other classes, it may be affecting people in those classes. So I thought I had already clicked on this, but not doing anything. There we go. All right. So, excuse me. Poor people at home weren't expecting that coming, were they? Okay. There's been a question on homework exercise, so let's hit that first before we get into chapter 12. So where was it? What was it?
Number 22 on
213. Oh, in this section. Okay. It's not. Oh, 213. Okay, no. We're in 313. Okay. 213. Got it. And which one?
Number 22.
Number what?
22.
22. Okay. 22. All right. This is page 213. Well, let me get my pen set up. All right. Page 213. This is problem set 8.2. And it's number 22. Okay. A pump is capable of developing 4 kilowatts of power. It's 4.00 kilowatts. And what does that represent? Just told you. Okay, wait. Its pump is capable of developing 4.00 kilowatts of power. That's the power. Capital P is the parameter we use for that. Okay. How many liters of water per minute can be lifted a distance of 35 meters? So the question is, how many liters per minute, and this is H2O. Oh, H2O, that's not a zero. Okay. Can be lifted a distance of 35 meters. So your H here is 35.0 meters. Okay. Now, they give you a hint here. 1 liter of water has a mass of 1 kilogram. 1 liter of water, H2O. I did it again. Okay. Mass of 1 point. Let's put the 2 significant digits here. Goodness, I'm going to have to go blow my nose, I'm afraid. Kilograms. Okay, that's the additional piece of information. Hold on just a minute. So sorry. All that sneezing loosens everything up. All right. Now, we're looking for liters per minute, which now we can measure in kilograms per minute. Okay. Now, there's two, one fairly minor, one not quite as minor, issues here. Okay? Number one, look at the power. It's in kilowatts. We need that in watts. Okay? Because the SI unit for power is watt. So how many watts is 4 kilowatts? Kilo means 1,000. So this is 4,000 watts. Okay? And that third digit, the second zero, the middle zero, is significant. The last one's not, but the 400, those three are. Okay? The other issue, okay, tell me first then, what is a watt? In basic units. Or, if not in basic unit, just what is a watt? How do you get watts? What does power measure? Okay, power measures energy per time. Remember digging out the patio in the backyard, and I worked for 8 weeks, and the Bobcat came in and did half a day and did as much work as I did. He had a lot more power. So this is energy or work, either one, per unit time. Say again?
I said I was going to say word, but
No, that's it. Now that's measured in, what do we measure either work or energy in? Yeah. Joules, okay. Joules per second. That's your time measurement. And that's what we got to change to minutes at some point. But we can get there later, okay? Now, what is work or energy? What is the work or energy? You remember what that is? In parameters or in units, it doesn't matter. Okay, especially work. Easy to remember work this way is force times the distance. Remember that? And then that's per second because power is per second. Okay? Now, next question, what is force? Now, by the way, the distance here that's being lifted is your h. This is your distance here. So we got that part. Okay? Your second is going to relate to the minutes over here, but we'll deal with that later. What is a force? Basic units of force. Think Newton's second law. Force is mass times acceleration, but the acceleration we're talking about here is acceleration due to gravity, times your distance, I'm going to put it as height, over seconds. That's, actually, I should be putting this over time, okay, because these are parameters, they're not units. So I sort of mixed them up there. Okay. Now that h is height, this one over here. Okay. Now we have everything down to the basics, okay? And what we're looking for is mass per time. They're asking for liters per time, but that's the same as kilograms per time. So this, if we can isolate that, we've got it knocked, right? So what we have is the power which is 4,000. And the basic unit for watts is kilogram meter squared per second squared, because a mass is in kilograms, acceleration is in meters per second squared, and height is in meters, so that gives us meters squared per second squared. And then this is per second, okay? That's what your watts are. These are your joules per second. Okay, now actually, time out. Let's go back to this formula. I should have done this first. Power is equal to, back to what we have here, mass times acceleration due to gravity times height divided by time. Okay? We're looking for mass per height. That's what the question is, mass per time. So what we need to do is divide by G and divide by H. Divide by G and divide by H. That wipes them out over here, okay? And that's going to give us mass per unit time, okay? So now I'm going to plug in. So there is your power. Divide that by acceleration due to gravity. Anyone know what that is? Oh, we use it all the time, huh? 9.80. And that's in meters per second squared times your height, and that was your 35.0 meters. Okay. Now, notice what happens here. This meter times meter is meter squared. There those go. And here's your per second squared. There it goes. And what you're left with is kilograms per second. Okay? So that's what our answer is going to be here, is in kilograms per second. And here's Haley. I don't know. Usually Sharon's here first. Now, she has been having a lot of problem with her sciatica. Is that how you say it? She was telling me something about a lot of pain down her leg, and it has disabled her a couple days, but not the class day yet. Maybe that's happened this time. But I also got your test graded, so let me give that back to you now. All right, we're doing example problem 22 on page 213. That's in section 8.2. We're just about where we need to be, where you've got this in kilograms per second. So if someone with a calculator will punch those numbers in for me. 4,000 divided by 9.8. And then that answer divide by 35. Now, 4,000 divided by 35 is going to be close to 100 divided by something close to 10. It's going to be something pretty close to 10 kilograms per second.
It was 11.6.
11 point what? 6. So 11.6 kilograms per second. Okay, that's what our units came out to. Now I'm going to, I need more room to write. Let's do it here. 11.6 kilograms per second, which is equivalent to 11.6 liters per second, because a kilogram of water is a liter of water. Okay? So there's our liters per second, but we need to get that into liters per minute. That's what the question asked for. So we're going to have to multiply by a conversion factor to get us blank liters per minute. Okay? Now the first blank stands for numbers. Where is it? Right here. See, 11.6 is your first blank over 1 units liters per second. We're going to multiply. Don't mess with the numbers yet. Put the units in their place first, and then we'll get liters per minute, and we'll later figure out the numbers that go here. So first, put the units in their place. What unit goes where? We're changing, the liters don't change, so don't mess with that. But seconds are changing to minutes. So how do we do that? Always put the units in their place. If you need a light on, you can turn it on. Okay. I can see well up here, but I don't know if y'all can see well back there. So what units go where? Changing from seconds to minutes. So one of them goes on top, one goes on the bottom. Which unit goes where? Say that again.
Time go on the bottom?
Well, time is on the bottom in both states. So it's not time. It's units. Seconds or minute. One goes on top, one goes on bottom. Which one goes where? They're both units of time. Make a guess.
Minutes on the bottom.
Minutes on the bottom. Absolutely right. And you can see that because that's where they wind up, on the bottom. Seconds goes on top. That's so you can get rid of the seconds. Right? Now, match the numbers with the units. Okay? How many seconds in a minute or how many minutes in a second? 60 which? 60 seconds is 1 minute. So 60 seconds, 1 minute, and now that means you multiply numerators, divide by the denominators, but that's 1. So 11.6 times 60. That would be a 6, 9, and 6. 6.9, no, 696, right, isn't it? Yeah. I put my decimal in the wrong, oh, my eraser didn't pick up. 696 liters per minute. And hopefully all three of those are significant. Because you're multiplying 60 times something greater than 10, so that should be something greater than 600, which it is. 696 liters per minute. Now that answer is not in the back of the book, but I feel very confident on it. You see how that works? And why it works that way. Okay. Units are your friends. Let them help you. The key here is recognizing a liter is a kilogram. And once you got that done, then your liters per minute, your units told you your mass per unit time, but that was going to be in kilograms per second, not kilograms per minute. So at the end, we had to do our conversion there. We could have done it earlier, but it seemed like that would just fog the issue badly. So, any others?
I was trying to find one similar to number 9 on the test.
On the second test? Okay,
I couldn't find a good one.
Okay, let me find the second test here. Okay, number 9. Is that the one you said?
Yes, sir.
9. A pile driver? Oh, come on. We've done several like that, haven't we? Okay. Not exactly like it, but awfully close. All right. So this is work and energy. There's a pile driver right there. Now, the thing that's going to give us a problem is their shortcut. And you don't need to take the shortcut. Okay. Okay. The issue here is the units, basically. Most of your examples are in SI units. The few that are in U.S. customary are not particularly helpful here. So let's just go back to our basic formulas rather than trying to model. Okay? All right, to erase the one I got here. Okay. Now, what I think I'll use all right, let's use number 6 on page 224. Okay, so page 224. Problem set 8.4. And we're going to modify number 6. So this won't be in the back of the book anyway. Now, we're going to modify it to match the one we've got here. Here we have a pile driver weighing, we'll go on and call it 975 pounds. So what is that a measure of?
Weight.
Say again? Weight. So that's called F sub W. I kind of like that. Most of the time I call it W, but F sub W reminds you it is a force. Okay? And this force, the weight is 975 pounds. Okay? Now, so that wasn't in the problem in the book. I'm putting it in. Okay? It says it falls from a height of 45 feet. Well, that's the one on your test. We're not going to do that. We'll use one in the book there, 1.75 feet. So that's your height is equal to 1.75 feet. Well, that's not very far, is it? So let's at least have it, let's make it 17.5 feet. Is that okay? All right. That'll make it a little closer, but not really all that close to what the one is on your test. 17.5 feet. So we're really changing the problem big time. Okay? And then the question is, find the velocity as it hits the pile. Isn't that about the same? Find its velocity as it hits the pile, right? So we're looking for V. This is the unknown here. All right. Now, if this were SI units, and you had that mass rather than weight, that's a really easy problem because of a little formula for it. However, this isn't mass, this is the SI units, so we're going to have to go from our basic assumptions, okay? What that means is draw you a little picture, okay? Here's a pile driver, it's in this chute, here's a pile that's in there, and the weight of this, F sub W, is equal to 975 pounds. Okay? Now, here's the pile way down here. Okay? And the distance between here is 17.5 feet. Now, that's what we usually call H. Okay? Now, as you can tell by the title of this section, 8.4, it's work and energy, okay? And 8.4 specifically is, if I can find it, conservation of mechanical energy. And mechanical energy, does anyone remember what that is? Mechanical energy is the sum of gravitational potential energy plus kinetic energy. So up at the top here, what is the energy of that pile driver? There's two kinds, gravitational potential and also kinetic. We're going to do it at the top and we're going to do it at the bottom. Gravitational potential and kinetic. Okay? We're starting at the top. What is the gravitational potential energy of that pile driver? Anyone remember the formula for gravitational potential energy? There are a couple of them. I'm going to give you a hint here too. What is the formula for weight? Can anyone tell me that one? That's a really basic one that we had. I can't remember if it was this chapter or the previous chapter, but what is weight? Force due to weight. It's one we've already talked about today, but we didn't call it weight.
Mass times the acceleration due to gravity.
That's it exactly. This is the mass times the acceleration due to gravity. Okay? Now, does that help you remember what gravitational potential energy is? It starts off that same way, but adds one more thing. Not adds, multiplies one more thing. The height is mgh. But in this problem, we don't care about m. We don't even need to know g. We already know the weight. The weight is F sub w. So that's the gravitational potential energy there at the beginning. Now that pile driver is just hanging up there because you haven't released it yet. So what's the kinetic energy of that pile driver up there at the top?
It's going to be 975.
No, wait. Kinetic energy.
Oh.
What is the kinetic energy of the pile driver at the top? Zero, because it's not moving. Kinetic energy is 1/2 mv squared, and since there's no velocity, this is zero. This is at the top. Okay? This is at the top. At the bottom, that's a different story. Okay? But all your mechanical energy is in potential energy at the top, and we know exactly what it is. 975 times 17.5. That's exactly your potential energy at the top. And that's your mechanical energy at the top because kinetic energy is zero. Now, conservation mechanical energy, if that's your energy at the top, that's also, so let's go and write this, E sub m for mechanical energy. Fill me in. 975 times 17.5.
17,062.5.
Okay, a little bit slower.
17,062.
0.62?
Yeah. 0.5.
Okay, let's make it 3 then. Okay, and that will be in foot pounds. No fancy unit here, foot pounds. That's mechanical energy at the top. Guess what? That's also the mechanical energy at the bottom because mechanical energy is conserved. 17,063 foot-pounds. Mechanical energy is conserved. Now, in reality, there's a little bit of loss due to friction, but we're not going to count that. Now, what's the gravitational potential energy at the bottom? Which is your zero reference level. Zero. So this is zero down here. So what is your kinetic energy at the bottom? Mechanical energy is gravitational potential plus kinetic, right? So then if there's no potential energy, it's all kinetic. Okay? Now, this is a little bit harder to deal with because now we've got to introduce slugs. Okay? If you have 17,063 foot-pounds of kinetic energy at the bottom, and you need to know velocity, here's your formula. I'll just keep it this way. E sub k at the bottom is 1/2 mv squared. Well, we've got to figure out how many slugs 975 pounds is. So that's another problem, okay? So what's the formula for, well, you just gave it to me. The weight is this, and that's mass in slugs times acceleration due to gravity. And the U.S. customary system, what's the acceleration due to gravity?
In the U.S.?
Yeah.
32.2.
Okay? So what we have here, the mass in slugs is equal to 975 pounds divided by the acceleration due to gravity, 32.2 feet per second squared. Not that that's that, well, it is sort of. Okay, so do that one. 975 divided by 32.2. Yeah. You know what? I just realized we could have done it the easy way. But this doesn't hurt us to do it this way. I was trying to avoid slugs is what it was. What does that give you? Say that one more time.
30.3.
Sounds reasonable. So the mass is 30.3. So this is 17,063 foot-pounds is equal to, and what we're going to do, multiply both sides by 2 and divide both sides by your mass. And what did you say it was? 30.3. That's slugs. Okay? Sorry about that. Okay? And that's equal to, well, that'll pretty much do it for us. Because, okay, you multiply by 2 too.
Yeah.
2 times 17, yeah, okay. And what was it? 1,126.3. And that will be in, and I didn't keep up with my units here. A pound is a slug foot per second squared, and the slugs go out. The feet multiply, so it's feet squared per second squared. But that's your v squared. How do we get v?
Square root.
Take the square root. So the square root of that is something on the order of 30-something?
33.6.
33.6. And you take the square root of the units too, that would be feet per second. Just at the end of this, realize we could have used a simple formula. If you go back to that section 8.4, and one of the formulas that comes out of that, it's on page 219, and we could have used it. V is equal to the square root of 2GH. Well, I was thinking that was only good for metric, or SI. It's not. It's good for them all. Okay, before you sit down, Brianna, here's your test. No, you don't have to come up here. I would have taken it to you. Has anyone heard from Sharon?
I thought she was.
Yeah, I'm afraid she may be having or sciatica problem, but I don't know that for sure. I'm just guessing. So let's see if this will work here. Here it's the square root of 2, but we use the U.S. customary, 32.2, and the height was 17.5. Okay? And the 32.2 was feet per second squared, and this is in feet. So this should give it to us too. 2 times 32.2, that's 64.4 times 17.5. Did you get the same thing as before? 64.4 times 17.5. Did you get 1126.3?
I got 1127.
Okay, 1127, and then take the square root of that.
Yeah, 33.6 this time. Yep.
Same thing. So we didn't have to go through all that, but it didn't hurt, did it? Not too much. Okay. All right. Oh, I forgot to mark Brianna here. Let me find my pen. There it is. And get you as being present. All right. All right, so does that help? Okay. All right, any questions? Any other questions? All right, then we're ready to get back on today's. All right, so since we're here on these slides, let's just stay on the slide. All right, to erase? Okay. All right. We're at the top of page 312. We're in chapter 12, which is matter, as if that matters. 12.1 are properties of matter, and we've been talking about these. And remember we said that matter, let's take an atom, which is the basic unit of an element. An atom is made up of a nucleus, and in that nucleus are protons and neutrons. I put plus for plus sign, 0 for 0 sign. And there could be a whole bunch of them in there. Okay? And
I just have a question
yeah.
to this really quick. Is the school closed on the 4th? Or?
Yes.
Okay.
Oh, okay. I guess we should mention that, shouldn't we? Next week, yeah, that is first week of July, right?
Yeah.
Yeah. We have class on Tuesday, but there's no class on Thursday because 4th of July is a state holiday, and you're right, the college will be closed. No one will be here, okay? Not me, nobody else, okay? So don't come on the 12th, on the 4th. Now, that's a class, that's a state holiday. We don't need to make that one up. And by the way, tonight is the last night we go till 7, and starting on Thursday, we go back to 6:30. Right? Okay. We've made up the class I missed because of my eye surgery. Okay. So, here's this tiny, tiny, tiny little nucleus that's filled with protons and neutrons, which are pretty massive. So it's a really, 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 really dense nucleus. And flying around out here is this little bitty electron. I mean, so small, you can hardly measure a mass at all. It does have a mass, not very much. You can't measure a volume. It is just tiny. But it takes up just about the whole volume of the atom because it's flying around in all sorts of directions around that little bitty nucleus, which is very, very massive. Okay? So that's the setup that we have here. And a hydrogen atom has just one proton with no neutrons usually, occasionally it does, and then one electron. So that's all a hydrogen is. Okay? Now carbon, the other one they've been talking about a lot, carbon has, and I was going to say, if you do have a book, let's see if I can know why this is stuck where it is. Okay. If you do have a book, I was trying to find, looks like, I was thinking there was a periodic table here, but I don't see it here. Let's see if it's later in the chapter. I don't believe it is. I don't recall it being there. No, pretty sure it's not. Okay. But in the back of your book, back inside cover, you can find out. No, you can't. Huh. Goodness gracious. I thought they were at least have a listing of the elements. Now, maybe they're in an appendix. Let's see if they're in an appendix. Here's appendix B. Appendix A is your answers. Appendix B is problem solving. Appendix C may be our best bet here. Yep. There's your periodic table on page 694. If you got a book, 694, and you see carbon over there, which is in the second row, the right-hand side of the second row, and you'll see a mass of 12, but a number of 6. Okay, what that means, you have 6 protons. The number means proton. So 1, 2, 3, 4, 5, 6. 6 protons in there, but atomic mass of 12, which means you have also 6 neutrons. Okay, that's in that nucleus. Tiny, tiny, tiny little nucleus, but that means you got 6 electrons floating around. 2 of those electrons float around really close, like that. And then the next 4 float around further out. Okay, not that far out, but further out. The picture in the book is a lot better than mine. So anyway, you have 4 electrons floating around out there. Okay? 2 close and 4 further out. Now, the reason you know that is that they have to be electrically neutral. Okay? You have to have the same number of protons as you have electrons. You don't always, but for a neutral atom, you do. Hydrogen has 1 proton, 1 electron. Carbon has 6 protons, 6 electrons. Okay. Now, there's a guy mentioned here on page 312 named Ernest Rutherford. He was a physicist born in New Zealand, and he actually received the Nobel Prize for Chemistry in 1908, right at the height of his career. But he proposed in 1903 the radioactivity results from the disintegration of atoms, and because of that, he developed this concept of the atomic nucleus, basically. And that's what I was describing there with the protons and neutrons. Now, that's as much as we're going to do on the structure, the basic structure of matter, though we're going to come back and refer to it some. Now, that's on the microscopic scale, but the elements and compounds are a macroscopic scale. Now let's talk about strictly macroscopic. They say matter exists in 3 states. Now, a lot of books don't call them states anymore. They call them phases, okay? And actually, there's 4 of them, but we're not going to talk about the 4th one much. I'll mention it. Can anyone think what those 3 states or phases are? Solids, liquids, and gases. Anyone happen to know what the 4th phase or state is? It's not in the book. It's called the plasma. Now, in this room, we don't have any active plasma that I know about unless we turned on the light. One of those lights, those are fluorescent lights, they have plasma inside them, racing back and forth between 2 poles, you might say, and that gas, it's like a gas, but it's not. It's a charged gas. That makes it a plasma. We don't worry about that now. But we're going to focus on our solids, liquids, and gases. Okay? And that's going to be a good chunk of what we're going to talk about for a little while. Okay? First, a solid. Okay? A solid is a substance that has a definite shape and a definite volume. Okay, now here's why. Macroscopic solids. Let's go back to microscopic, the atoms and the molecules, you might say. In a solid, those atoms are put together in fixed places. We call it a crystal structure. Okay? Remember we talked about one last time? Sodium chloride. Sodium, a soft metal that's explosive if it touches water, and chlorine, a green poisonous gas that you don't want to be around, but you put them together, and you have salt that you put on your food. Okay? And you can eat, and it doesn't bother you at all, except maybe raise your blood pressure, but it has nothing to do with sodium or chloride. It just is a characteristic of salt. Okay? Now, what is happening? In a salt crystal, you have a sodium ion, a chloride ion, a sodium ion, a chloride ion, a sodium ion, yeah. They're fixed in position, and they're rigid. They don't move around. They do a little bit of vibration, but they don't translate, they don't do much else. They are fixed in position. That's why it has a definite shape. And their definite proximity, that's why it has a definite volume. A solid is a solid because of that fixed crystal structure. All those atoms have the place in the crystal. They don't really move around. They do vibrate a little bit, but that's all. All matter always moves a little bit. So, what is a liquid? And by the way, if you had a solid, think of a solid, and you wanted to make it a liquid, what are you going to have to do to make that solid a liquid in general? How do you make a solid? Say again?
Melt it.
I can't hear.
Melt it. Make the solid liquid.
Okay, my hearing said that. What was that?
Melt it.
Melt it. How do you melt it?
Apply heat.
Apply heat. Perfect, perfect, perfect. So, hang on to that concept. Okay? A liquid is a substance that takes the shape of the container in other words, it doesn't have a definite shape, but it does have a definite volume. An indefinite shape, but a definite volume. Now, what happened? You added heat, okay, or added energy. And when you add energy, remember I said those molecules in the solid, they can vibrate? You add energy, they vibrate faster and harder and stuff, and finally they break the bonds. They break the bonds that are holding themselves together, and then they melt. Now those molecules or atoms flow past each other. They don't have a definite shape, but they do have about the same volume because they still stay close to each other. So it has a definite volume. Okay? Then a gas. Now, how do you make a liquid into a gas? Anybody? Any ideas?
Evaporate it.
Yes, and how do you do that?
Apply more heat.
Apply more heat, absolutely, or more energy. So what's happening then, those liquid molecules that stay close to each other, so they have a definite volume, but they no longer have the crystal structure, but they're staying close to each other. Now you add more and more energy, they get more active, and now some of them fly out. They lose that definite volume. They now take up the whole volume of the container. So a gas is a substance that takes the shape of a container, just like the liquid, but has the same volume of the container. Okay, so in other words, the gas molecules are free to go wherever they want to. Have y'all ever dealt with ammonia? Never. Don't you know what it is?
You mean like in cleaning products?
Yes. Yeah. Have you dealt with that before? What did you notice about it first right off the bat?
The smell.
The smell, okay? And that's because ammonia, even though in the cleaning product it's dissolved in a liquid, if you open that pure ammonia up, if I were to snuck in a bottle of ammonia and take the lid off of it and say, I need to go downstairs to the office for a minute. Y'all just study here for a bit. After a while, if I hit it in the corner up here, Krishana's eyes would be burning and stuff like this, and in a short time yours would be too, because those gas molecules are filling the whole space. After a while, the whole room would smell of ammonia, right? Because those gas molecules don't have a definite volume and don't have a definite shape. They take the shape of the container, but also the volume of the container. Okay. Now, while we're here, I'll just mention the fourth one. I already named it. It's a plasma. How do you think you get a gas into a plasma? Make a guess.
Inject it?
Add more energy. It doesn't have to be heat. In fact, it's usually, well, it can be heat, okay? In those fluorescent tubes up there, that is they usually call it a mercury vapor, though some of them may have other substances in there. You have you have a really big thing. If you've ever seen inside those, they have this big box up there called a ballast. Now, that's a strange name for it, but what it is a very heavy-duty capacitor. What a capacitor is an electrical element that stores a lot of charge. And if you have a lot of charge, you have a big potential difference. In other words, a big voltage. So what is happening is you're setting up a big potential difference between two ends of that tube, and therefore the mercury vapor gas is flying back and forth, but there's so much energy given, it's no longer a vapor. Now, gas is now an ion, okay? What an ion is a molecule or an atom that has either had an electron stripped away or it stripped away an electron from somewhere else. So now it's charged. Either plus charge if it's lost an electron, negative charge if it's gained an electron. So that's what a plasma is a charged gas, and the charge comes from adding enough energy. You're either knocking off electrons or picking up electrons, one or the other. Now, here might sound like sort of a trick question, but it's not really. It's pretty meaningful. In the whole universe, what do you think the most common phase or state of matter is? Solid, liquid, gas, or plasma? Make a guess.
Plasma?
You're absolutely right. Why did you guess that? Any special reason?
No.
Okay. Let's think of just our solar system for a minute. What is the most massive object in our solar system? The sun, for sure. In fact, I teach it in a physical science class, and I can't remember. The sun itself is several thousand, if not million times more massive than all the rest of the solar system put together. All the planets, all the moons, all the comets, all the asteroids, all the everything else put together, the sun is at least a few hundred times more massive than all that. And yet the sun is not solid, it's not liquid, it's not even mostly gas, it's predominantly plasma, because it's such incredibly high energy. Of course, no solid is going to remain solid at that temperature. No liquid will remain liquid at that temperature, and most gases are actually going to become plasma. So if our solar system is made up mostly of plasma, yeah, what you need? What my words say? A solid is definite shape, definite volume. A liquid is the shape of the container, but the definite volume. And a gas is the shape of the container, but the same volume as the container. Okay. So, and then a plasma is just high energy, charged gas, basically is what it is. So, you've added more energy. And you're absolutely right. At least as we understand it now, most of the universe is made up of plasma. However, the scientists are discovering more and more and more of what they call dark matter, which they don't know what it is, but it's not high enough energy to be a plasma. So it's either solid or gas. It's probably not liquid, but it's one of the two. Okay. Now, let's leave. Can I leave this slide? Yeah. Okay. And go back to the other one and go to current slide there. Here is what I was trying to talk about. This is an illustration which I don't find particularly illustrative, but I guess it is an illustration. In a solid, the molecules are stuck in place. Now, if you picture this, you'll notice that this molecule is next to the dark blue is next to a dotted blue, next to a dark blue, next to, they never is a dark blue next to a dark blue, okay? They're always, and never is a dotted next to a dotted. It's always connected to a dark blue. This would be similar to what you would have in, now I don't want to say never, but in this illustration it's never. This would be similar to what you had with sodium chloride, okay? The sodiums are always connected only to the chlorines. The chlorines are only connected to sodium. You never have a chlorine to chlorine or a sodium to sodium bond. And what these represent are the fixed bonds, okay? That fixed in place, notice they're all about the same length, okay? Of course, you got some behind the others, so they look shorter, but they're all about the same length. But they do have this spring-like picture to them because they can vibrate a little bit. Not a whole lot, but a little bit, okay? Well, what happens when you add energy to that, usually in the form of heat, but it could be other forms of energy, then the molecules break apart. I mean, the atoms break apart, okay? And now they're not connected to each other, but they stay close to each other, okay? They stay that relative same distance apart, so they have the same volume, but they're free to fill the container. That one isn't free to fill a container. It's fixed by those fixed positions. Then when you add more energy to this, now these molecules leave that fixed position and are just flying through space, occupying the whole volume of the container, wherever that is. Every now and then they collide, and they show a couple of them colliding, but when they do, they bounce right back. They don't reconnect. They just bounce off each other. Here, they stay close enough, they're tightly bound to one another. In the gases, they are not. So that's what's happening on the microscopic scale of what's the difference between a solid, a liquid, and a gas. So, for the next little bit, we're going to talk about properties of solids, okay? So let's see this next slide. That's going to be several pages away, okay? Yeah. So let's go back to our white page. We'll go from current slide. All right. That wasn't Sharon that you were talking with, was it, Brianna? Have you heard from her? Okay. All right, let's look at some properties of solids. And actually, I was just talking about some. I hadn't used the term because I couldn't remember if this book talked about them or not. But these are properties of solids. I've got to get my pen back. There we go. Properties of solids. The first of these, and it's actually two of them, is cohesion and adhesion. Okay, cohesion and adhesion. Okay. When you see the prefix co, what comes to mind? Any word that leads off with a co. Think of cooperate. Second? Okay, it's doing things with one another, okay? So think of the preposition with, okay? So cohesion is the characteristic of a material to stick to other material just like it, with itself, cohesion, okay? Cohesion is the force of attraction between like molecules. Force of attraction between like molecules. Okay? Force of attraction between like molecules. Now, think of the word adhesion. Or, yeah, what does that mean? Okay. Well, how about adhesive? Isn't that pretty close? What does an adhesive do?
It sticks to something.
Yes, it sticks two unlike things together, like the Band-Aid on your skin, right? Adhesive tape, okay? That is the force of attraction between different or unlike molecules. Unlike molecules. That's adhesion, okay? Now, a few examples of this. I hope you haven't, but I'm guessing maybe you have. Ever seen mercury spill? Like a thermometer breaks and that silver fluid that's inside, you see it, or maybe some kid at school had some mercury from somewhere. Ever really paid attention to mercury? Ever seen it?
I've seen it in a video.
What's that?
I've seen it in a video.
In a video. What did you notice about it?
It didn't stick to anything.
It's what?
It didn't stick to anything.
It did not stick to anything. In fact, it forms these tight little spheres. They look like they're beads, but you touch them and they match because it's a liquid. But it gets as far away from everything else as it can. It's cohesion. It sticks together like crazy and doesn't want to stick to anything else. That's mercury is very strongly cohesive. Okay? Now, water is somewhat cohesive. I'm going to show you why. And I don't know if you remember this from much earlier. In fact, let me scroll. Oh, goodness, I'm going to have to get out of this to do it. But if you recall, you have two hydrogens and an oxygen. Okay? Two hydrogens and one oxygen. H2O. And they always draw them like this. Okay? They're never HOH. Okay? It's never one end of the molecule and the other end of the hydrogen. They're always on one side or the other. They're always sort of close to each other. Now, there's a reason for that. Just like if you remember, carbon had 4 electrons in the outer shell. Oxygen has 6 electrons in the outer shell. Okay, now this is getting a little more specific than maybe you really care for, but those electrons usually go in pairs, but they always occupy certain shells. I mean, certain, I'm having trouble thinking of good things to call it. Orbits, let's call them orbits. They have 4 orbits for those electrons. In carbon, each one takes its own orbit, some months at a time. In oxygen, there's 4 orbits, but there's 6 electrons. So 2 of the orbits have 2 electrons, and 2 of the orbits have 1 electron each. Okay? Now, we're trying to think of a way in space. Think of a ball, and if you want 4 places equally placed around the ball, you'd have 1 here, 1 here, 1 here, and 1 there. So that each of them makes a little triangle, and however you turn the ball with those triangles around it, it would settle out that way. Okay? So 2 of those are paired electrons, and they are adjacent to each other, and the 2 that have single electrons, they are adjacent to each other too, because they're each adjacent to everything else. Okay? That's why the 2 hydrogens, they connect with those single electrons. Okay? And that's why water is like this. Well, the hydrogens tend to be a little more positive, and the oxygen tends to be a little more negative, because it has more electrons around it than the hydrogen does. It hogs the electrons, so the hydrogens wind up with not as many electrons around that, so they tend to be a little positive and oxygen a little negative. Well, if every water molecule is like this, then the positive hydrogens always tend to pair up with a negative oxygen, and so on. So therefore, water molecules really stick together pretty tightly. Okay? Now I'm going to make a proposition to you. Water is, yes?
Miss Sharon texted me. She said she's wasn't feeling good today. She had a bad migraine.
Okay, say that one more time.
Miss Sharon told me to let you know she wasn't feeling good today. She had a bad migraine, but she will be Thursday.
Sorry. Okay. All right. Thanks. I knew something major had to be happening, because she's usually here very early and pretty serious about not missing class. So, okay, thanks for letting me know. All right. So water has this thing, and we call this hydrostatic bonding. Now, here's what my suggestion to you is. Oxygen has an atomic weight of 16. Hydrogen of 1 each. So oxygen has a molecular weight of 18. If you look up all the other molecules in existence in nature and label them out there, you would find there's not a single molecule that's anywhere close to 18 molecular weight that's not a gas. Most things, even carbon dioxide is 44, and many of the others are even heavier. Water is one of the lightest molecules, and yet it's a liquid. It's not a gas. The reason is this hydrogen bonding. Okay? So water molecules have a certain amount of cohesion too. But then because they have that hydrogen bonding, they'll stick to anything else too, so they're also really good about adhesion. So water will cohere, but it'll also adhere. Mercury, it coheres like crazy, doesn't want to adhere to anything else. Okay. Now, there is an exception to that. I don't know if you've ever seen it. I remember there were some kids, I don't know where they got the mercury. They shouldn't have had it, but we didn't know it was that dangerous. They would bring that mercury, and you could put a penny in that mercury, and because this is a metal, the mercury would adhere to the penny, and it would make it look just like a dime, because mercury is very silvery looking. and you would think that penny was a dime then because it was so silvery looking. Just was a little big for a dime. Okay. So there are some things that mercury will adhere to, other metals being one of them. All right, I'm going to erase my ugly little water molecule. Okay. I was just showing why water coheres very well too, but it also adheres, and the reason is that same hydrogen bonding. Okay, another property of solids is tensile strength. Okay, now again, you can have different degrees of this. What does the word tensile mean to you? Any idea? Think of another word that sounds like tensile.
Just makes me think of utensil.
Say again?
Like utensil.
I hadn't thought of that one.
Is it relating to tension?
Say again?
Is it relating to tension?
Tension, exactly. That's the one I was thinking of. And it may be a utensil is similar to that too. I just hadn't thought of it in that term. It's related to tension. Tension is the ability to be pulled. Okay? So tensile strength of a solid is a measure of its resistance to being pulled apart. Measure of resistance to being pulled apart. Okay, now here's my guess. I was thinking of this when you said it. Utensil is something, if you think all utensils, like eating utensils, are elongated. And I think the way they make them is trying to pull them apart and stretching them out in a certain direction. I'm just guessing if that's where the name comes from. May be wrong, okay? But it's the measure of the resistance to being pulled apart. All solids have this to different degrees, okay? It's not really a solid, but have you ever had a piece of that hard candy they call taffy, and you try pulling it? You can ultimately pull it, but boy, it's hard to pull apart. Whereas if you had divinity or something like that, it breaks apart really easily. So it's the tensile strength is the measure of the resistance to being pulled apart. Okay? And they have, they say tensile strength is the ratio of the force required to break a rod or a wire and the cross-sectional area of that rod or wire. You don't need to know that formula, but there it is if you need it. Another characteristic or a property of solids is hardness. Now, that is the measure of the internal resistance of the molecules to being forced apart or closer together. The measure, I can't write, of internal resistance to being forced further apart or closer together. Okay, now it almost sounds similar to tensile strength, but it's not, okay? Hardness is how much give it has, basically, okay? They have a thing mentioned here, the Brunel method, named after Johann Brunel. He was an engineer and metallurgist born in Sweden, and he invented the Brunel machine for measuring the hardness of solids. Okay? That's sort of interesting, and they do show a picture of this in the book, but you don't sweat this. They also have the Brunel value or number is the ratio of the mass placed on the object in kilograms and the surface area of the impression in square millimeters. So I'll just put as a subtype Brunel. I can't write. I can't spell. Okay. I was getting my L's before my N's. And they also call it a Brunel ratio, I think. Brunel number or value. But you don't need to know that too much. Here's something to me that's a lot, I think, more common, and I'm surprised the book, I just glanced again to make sure it wasn't in here. But in my physical science book, they talk about the Mohs hardness scale. And this is really common. The hardest material, naturally occurring material, and I think it may be the hardest known to man, unless they've made some super duper synthetics that are harder, is diamond. You don't get any harder than diamond. Okay? And then after that, there's several. There's a scale of 10, and diamond's a 10. I can't remember what 9 is. 8, I think, is corundum or something like that. And then 7, it goes on down. The softest is talc, T-A-L-C. And I'm guessing you ladies may have at some time in your life dealt with talcum powder. Yes? Say again?
I don't know what that is.
Okay, talcum powder?
I've heard of it.
How about baby powder?
Yes.
Okay, look at baby powder, and you'll see one of the main ingredients in there is talcum powder. You can't get much softer than that, can you? Okay, there's no grittiness about it at all. Incredibly soft. So that's the number 1. Diamond is the number 10. Everything else is in between. Your fingernail, I think, is about a 3.5 or 5.5, something like 3.5, I think. So everything can fit on that Mohs hardness scale. You don't need to know that either, but just hardness is another characteristic of solids. Okay, and it's funny, I was mentioning cohesion and adhesion, and I was mentioning liquids there. They also have that, but solids do too. Okay, another one, number 4, and you all have to know the numbers, ductility. Ductility. The property of a metal that enables it to be drawn through a die to produce a wire. The property, and mostly of the metal, it says, not just any solid, of a metal to be drawn through a die. I'm going to abbreviate like crazy. Now, I don't know. A die is not one of those two things that you throw on the thing and call them dice. That's not that die. This is a hole. And, okay. D-I-E, right. Okay, it's not to quit breathing either. Okay. But it's the same word. I mean, same spelling. Okay. To produce a wire. Have any of you ever seen, I was going to say spaghetti, and maybe it is, though I've seen the spaghetti made a different way too, but how about Christmas cookies? Have you ever seen those things you put on the end of a plunger and you force the colored sugar through it and it comes out in squiggles? You know what I'm talking about? And you can either dot them on things or you can make different patterns with them. My wife does Christmas baking and she has one of them. That's the ability to be extruded through something. Now, Christmas sugar cookies are not solids, but it's the same type principle, okay? To be drawn through a die to become a wire, okay? Another one here is malleability. Yeah, malleability, okay? It's M-A-L-L-A, no, M-A-L-L-E-A-B-I-L-I-T-Y. Ability is the last part, M-A-L-L-E is the first part, okay? And what that is the property of a metal. These are getting into metals now. To be hammered and rolled into a sheet. Okay? Can anyone think of a metal that shows up as sheets? If I say another word for sheet, you'll immediately think of it. Foil. Aluminum. Aluminum's a metal, isn't it? Okay? I wouldn't be surprised if there's not some aluminum in the room here. Okay? Well, you can roll out aluminum thinner and thinner and thinner until you get it into basically aluminum foil. Gold is another one like that. Have you ever heard the term, a term is gold foil, but there's another term, what do they call that? Gold, oh man. It's a very, very thin film, and you can just rub the gold onto, say, a wood or something, and it looks like it's gold, but it's really wood. Oh, there's a name for that. I can't think of what it's called. It basically is that. But that's what malleability is. It's a property of a metal to be hammered or rolled into a sheet. So all the same thing from above. Property of a metal to be. And then this starts off hammered or rolled into a sheet. So like foil. And actually they do this even with steel. If you've ever seen a steel plant at work, they just heat up the steel really, really hot, and then they can roll it into sheets. And you get sheet metal, okay? So even steel.
Did you say
sheet, S-H-E-E-T. Okay. Like, yeah. Do you know what I mean by sheet metal? Yeah. This right here is metal, and it's very thin metal. It's been bent and creased into a sheet and bent over. That's sheet metal, and that's the ability. That's malleability for that to happen. Okay? Now this is one I think we mentioned earlier in a different context, elasticity. Now this is definitely not just a metal. Elasticity is the measure of a deformed object's ability to return to the original size and shape. Measure of a deformed, sounds so weird, doesn't it? Object's ability to return to its original size and shape. Say again. Objects, OBJ abbreviated it. Object's ability to return to its original size and shape. Now, I can't think if I gave you this example before or not, but it's one that I recall pretty vividly. Have any of you ever played volleyball? Okay. Now, I don't know if the volleyball you played with was regulation or not, but a regulation volleyball is fairly hard. I mean, yeah, it will bounce and stuff, but it is pretty hard, right? It's not something, well, my illustration's going to get, okay. I was on a intramural team. It was a co-ed team when I was in school, grad school in Nebraska. And we had this one really tall gal who had played volleyball in high school. She was pretty good. She was a really good spiker. And she had this good friend who had also played in high school who was a really good setter. And they were the main components of our team, you know. We had some guys that were pretty good and other gals that were okay. But, boy, if we could get the ball to those two, that setter could set it up for that spiker. Well, was one team we played this one night, they had a taller girl than we did, and she was a little bit better than ours. And she had a setter who could just set it up perfectly. So we were pretty well matched, but outmatched. And you know, when you're playing volleyball, you sort of, both teams rotate in opposite directions. So at some point, you're going to be across the net from everybody else, you know, at different times, you know. Well, when it came my turn to be across from their spiker, and boy, she could spike. We were watching them when they were warming up. Her setter could just set it up perfectly for her, and she could get way up in the air and come down with a bullet, you know. So I knew it was coming. You always knew it was coming. Whatever we did, they'd get it to that setter, she'd set it up for the spiker, and that spiker would then hit it. Well, I was across the net from her, okay? And I knew it was coming, and sure enough, it went over a couple hits, and then that setter set it up just perfectly for her. So I went up with my hands as far up as I could go and tried my best to do everything I could to block it, you know, because I knew it was coming. Well, she had a real down angle on it. I was already up there, and it came and hit me square in the face. Okay? Now, I'm serious here. I felt that volleyball touch both ears at the same time. Okay? That ball deformed across my face. Then it bounced back to its original shape because of its elasticity. Same thing with every ball. I think I mentioned before, you hit a baseball with a baseball bat, that ball deforms and wraps around the bat just instantaneously, but then returns to its original shape. That's what elasticity is. The measure of deformed object's ability to return to its original shape. Now, my finger isn't particularly elastic, but I can press on the corner of this desk, and when I pull it off, there's a dent in my finger. But you wait a little while, and that dent ultimately goes away. So it does return to its original shape. So that's elasticity. Now, there is a graph they often show, and it's called the elastic limit. This book doesn't show that, but I'm going to leave this graph here because I filled out the page anyway. All right, to delete this? Okay, so I'll discard this and go back to this one. Okay. Let me get my pen back. Boy, this is so bizarre. Okay, here's a spring. Now, I don't know if you think of a spring, I hope you do, as being elastic, but a spring is in that shape right there, okay? Now, this looks a lot like the one that's on our garage door opener, because I've had to replace it before, and those are not easy to work with, okay? So that spring. Now you can pull the spring, and as long as you pull the spring and do not exceed its elastic limit, when you release, it's going to go right back to that original shape. Every time your garage door opens and closes, it's going to go back to the original shape, right? But, I don't know if you've ever done this before, if you stretch the spring until the term for it is sprung it, then you've exceeded the elastic limit, and you release that, and it stays in this deformed shape. Okay? So this one is going to spring back to this one is not. You've exceeded the elastic limit. Now you've gone into what they call the plastic range. Elastic is when it goes back to its original shape. Plastic is when it doesn't go back. Now, if you stretch it even further beyond its elastic limit, then you'll actually break the wire or the whatever the material is. Okay? So you can deform an object. If it goes back to its original shape, that's elastic. If it doesn't go back, that's plastic. They don't mention that here. But then, if you stretch it even further, you rupture it or break it. Now, there are some materials that will actually rupture before they go to plastic. They'll be elastic for so much and then they break. They don't even go to the plastic stage. But that's what elasticity is. Now, I think I will give that formula to you, okay? And that one is this one. The stress is the force you put on it, okay? And that's equal to the applied force divided by the area over which it acts. Okay? Now, that's in sense of you can use that in terms of elasticity, but you also use it in terms of other things as well. And that's what we're going to talk about next. There's some of these other things. Okay? Now, what is our normal unit for force? SI unit for force. Named after Sir Isaac. Huh? Newton? Is that what you said? Yes. It's a Newton. Okay, what's our SI unit for area? Well, how about length? Meter. And area would be square meter. Now that is a really bizarre SI unit, okay? Because a Newton is considerably less than a pound. A square meter is approximately, if you'll take a look here, the area of this door from the handle to the floor and about the width. That's about a square meter. That's a big area for a very small force. So a stress is measured in newtons per square meters. Those numbers, that unit is a tiny, tiny unit. So the numbers get to be quite large units, quite large numbers. Now this unit, a newton per square meter, has also got a name named after a guy, Blaise Pascal. So its unit is PA. They already had something else whose unit was P, so they used the first two letters of his name. Capitalized the first one, but didn't capitalize the second. That's a Pascal, a Newton per meter squared. Okay? And it's an incredibly, incredibly tiny unit. Okay? Now, you also measure other things in terms of Pascal. One is, have you ever needed to measure your tire pressure?
0.094.
one more digit would be 38, wouldn't it? Because you have 3 digits there, 3 digits there, 3 digits there. Okay? That would be newtons per square centimeter. Okay? Well, we don't want square centimeters. We want square meters. So I'm going to have to put my conversion factor in here, and this will be newtons per square meter. Okay? Now again, the first blank is for numbers. Don't mess with those yet. The second blank is for units. Put the units into place. Notice that newtons are same on both sides of the equality sign, so you don't have to mess with that. But your centimeters squared are changed to meters squared. So we need to make that conversion. What's going to go on top and what's on the bottom? Let's first just deal with meters and centimeters. What goes on top, what goes on bottom? Say again? Okay. We're doing a conversion from newtons per square centimeter, which is what we measured that in, to newtons per square meter, because that's what a Pascal is. So we're trying to get this into pascals. So we're trying to go from newtons per square centimeter to newtons per square meter. So I put my conversion factor here, and this is for numbers. These are for units. That's for numbers. Don't worry about the numbers yet. Deal with the units. Newton stayed the same on both sides, so you're not dealing with units. What's changing is square centimeters and square meters. So let's just first deal with meters and centimeters. Which of those is going to go on top, which is on bottom? Meters or centimeters? Meters goes where? Second? Yes, meters go on the bottom and centimeters on top. So let's just put the thing. Meters on the bottom, centimeters on top. Now, before we go any further, they're not going to square them yet. How many centimeters in a meter or how many meters in a centimeter? Does anyone know? Second? Oh, we should know that. How many cents in a dollar? Cents? Say again? 100. So there's 100 cents or centimeters in 1 meter. Okay? But we're not dealing with meters and centimeters. We're dealing with square centimeters and square meters. So you have to square the meter, square the centimeter, but you also have to square the 100 and square the 1. Okay. Squaring 1 is easy. That's still 1. Squaring 100 becomes 10,000. You double the number of zeros from 2 zeros to 4 zeros. Now the centimeters squared cancel out and you get newtons per square meter, just like what you want, but then you move your decimal place 4 places to the right. 1, 2, 3, 4. 938 newtons per square meters, which would be 938 Pascal, because Pascal is a newton per square meter. Okay. Now, let's take that brick and put it up on its edge. Okay. Its pressure or stress or whatever you want to call it is still the force, F sub W, the weight is still 12.0 newtons. Still the same. Per unit area, now the area being covered is 6 by 8, which is 48.0 square centimeters. Okay? And if you divide 12 by 48, I think I can do that one in my head. That's 0.25 newtons per square centimeter. And do the same thing we just did before, multiplies by 10,000, so you move your decimal 1, 2, 3, 4, so put 2 more zeros on it, and you get 2,500. That zero is significant. Newton per square meter, which is, I can't write, 2,500 pascals. That's a pretty big number, isn't it? If we wanted to write a smaller number but a bigger unit, what could we do? I've asked this just about every class. What is the metric prefix that means 1,000? One of you's already answered that. Second? Kilo, you got it. So you could call this 2.50 kilopascals. Kilopascals. And that, now that 0, you don't have to put a bar over it anymore because you know that's significant. Okay. So you went from 938 Pascal to 2,500 Pascal just by turning it up on edge. There's a lot more pressure on the plate from the second block than the brick than there is on the first one. Now, sort of a dumb example of that, I'll give it. I was dancing with my darling, okay? And she was wearing spiked heels. And she accidentally, or I messed up, and she stepped on my toe with her spiked heel. Gonna hurt a little or a lot? I would say a lot. Why? Because my darling weighs a little something, right? And all that weight is on a terribly small area, the spiked heel. That's going to be a lot of stress, pressure on my foot. But I was dancing with my darling, same darling, by the way, but this time she has on tennis shoes. And I mess up again, and she steps on my foot again. Is that going to hurt just a little or a lot? A little, because now the heel on the tennis shoe is about like that. A much bigger area than that, okay? The spike heel. It's going to be a big, 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 big difference, okay? And that's what they show in the book here, too. And let's see. I don't think they show this on the slide. No, they don't. I guess I'll go to, all right, to escape this and go to my white sheet. Oh my goodness, we're almost out of time, aren't we? How time flies when you're having fun. Okay, let me see. I'll just escape here. And we'll go back to this one. This may be the last one we're going to have time for tonight. Okay? What we have here is a 160-pound woman. Okay, let me get my pen back. What does that a measure of? 160 pounds. What would she call that? Her weight. That's F sub W, the force due to her weight. Okay? Now, let's say she rests her weight on a 4.0 square inch heel. Now that would be a typical flat shoe, okay? About 4 square inches. So the area is going to be 4.0 square inches. Okay? What would be the stress then? Stress is equal to force per unit area. We're also going to call that pressure later. Okay? And that is 160 pounds over 4.0 square inches. And that's going to be, I think I can do that math, 40 pounds per square inch. Okay. That's ugly. Let me see if I can make that look a little bit better. Let's try that again. Pounds per square inch. Okay, and that's also called 40 PSI, pounds per square inch. Okay, but unfortunately, she's going to change her shoes and go to a spike heel, a pointed heel. And this pointed heel, this is for the, I'm going to call it sneaker, though it could be a little bit better than sneaker, but that's area for the, oops, maybe I shouldn't call it sneaker. Let's call it flat shoe, F, okay? This will be the spike heel, okay? And that's going to be 1/4 of a square inch. So the stress now on my poor foot is force per unit area, and that's 160 pounds per 1/4 of a square inch. I don't know if you remember how to divide fractions. Do you remember how to do that? You invert and multiply. That would be 160 pounds times 4/1. And the square inches goes with the 1. Okay. So this will be 640 PSI. So you go from 40 PSI to 640 PSI. That is a huge, huge difference. Okay? And by the way, this 0 is significant here. That one's not. Okay? So you go from 40 PSI to 640. That's the multiplied effect of 16 times. Okay? So you see the pressure or the stress is much, much greater on the tiny. Okay? Now, something similar to it, if you were dealing with a 65 kilogram woman, what's that a measure of? Anybody know? 65 kilogram would be a measure of? No, it isn't. Mass. That's your mass. You have to get that to weight. How do you get that to weight? How do you get it to weight? What's the formula?
Mass times
Acceleration due to gravity. You multiply that by what? 9.80 meter per second squared. And that would give you 65 times 9.8. That's 640 or 30 what? Anyone do it? 65 times 9.8. Anybody? Say again.
637.
37, okay. 637. What units? Newtons, exactly. Kilogram meter per second squared is a Newton. Sorry. Must have swallowed wrong. Now, on the first case, that's going to be a 25 square centimeter heel. That would be equivalent there. So the area of the, what they call it, her flat shoe, was going to be 25 square centimeters. So what would that give you? The stress would be 637 newtons divided by 25 square centimeters. And that would be what? Anybody?
25.
Second?
25.40.
25.4? Is that what you said?
40.
4.8? Okay, 4.8. Okay, we'll keep that for a bit. And that would be newtons per square centimeters, but that's not a Pascal. Again, we'd have to multiply that by 10,000. Remember, we did that conversion earlier. That means moving it 4 decimal places. That would be 254,800. 254,000 Newton per square meter, which would be 254.8 pascals. Okay? No, kilopascals. Okay? And they rounded in the book because we only have 2 significant digits, 250 kilopascals. So you see a PSI, it's not the same as a kilopascal, but at least is a similar unit. 40 PSI, 250 kilopascal. Okay? Pounds per square inch, newtons per square meter. Okay? Takes a whole lot more of them. Now, for the spike heel, that's going to be 1 square centimeter. So the area of the spike heel is going to be 1.0, do they call it? Yeah, 1.0 square centimeter. So that would give you 637 Newton per square centimeter. And you'd have to move your decimal 4 places. So you do 1, 2, 3, 4 zeros. That would be 6,370,000 Pascal. Goodness gracious. That would be 6,370 kilopascals. You could even say 6.37. They probably rounded to 6.4. Yeah, 6.4 times 10 to the 6 pascals. Huge, huge number. Okay? Or 6,400, like I said, 6,400 kilopascal. They rounded it to 2 digits. All right. I think we've run out of time, haven't we? And sadly, this is our last day of going till 7 o'clock, so we're not going to be able to go as late next time. But we'll start next time with tension. We already talked about tensile strength. We're now going to talk about tension. Okay? Wait. What we're talking about are different types of stresses. Stresses are force per unit areas, and we'll talk about different types of stresses. We'll talk about tension, compression, torsion, and bending. Those are all different types of stresses. So we'll begin that on page 318. Let's see if we got far enough for any homework exercises. Not really. We didn't. We just did some examples. So we'll pick up those homework exercises next time. Okay? And so all basically we did today was 12.1. We didn't get out of 12.1. Sorry about that. I guess I talked too much. No, we didn't. Wait a minute. We're in 12.2, aren't we? Yeah, 12.1 didn't have any homework exercises. Okay, so we went from 12.1 to 12.2. Okay. But no problems in 12.1. All right, we'll see you then on Thursday. Okay? And next week, no Thursday. But this will have class Tuesday, Thursday, then we have Thursday off. Good deal.